So, engineering thermodynamics, unit 4, ideal and real gases and thermodynamic relations. So, what is mean by ideal gas, real gas, and what are the thermodynamic relations in between them? So, first we go for the basics. Concepts of ideal gases. In thermodynamic, ideal gas law is well defined approximation of the behavior of many gases under the diverse conditions. Ideal gas equation is the combination of empirical laws, that is called Charles law, Boyle's law, Gauss-Lagrange's law, Avogadro law. So, these are all the law which emphasize the concepts of ideal gases. So, next we go for the characteristics gas equation. The general gas equation for ideal gas is given by PV divided by T equal to constant. So, P is the pressure in Newton per meter square and V is the volume in meter cube and T is the temperature in degree Celsius. So, taking R as a constant, therefore, PV divided by T equal to R, PV equal to RT. The mass of the gas M is considered as the equation state becomes PV equal to M into R into T. This equation is known as the characteristics gas equation. So, for that, ideal gas equation is the equation defining the state of hypothetical gases expressed mathematically by combination of empirical and physical constant is also called as the general gas equation. So, equation of ideal gas, the state of an ideal gas is determined by the macroscopic and microscopic parameters like pressure, volume and temperature, right. So, PV equal to N into R into T. So, P is the pressure of the ideal gases, V is the volume of the ideal gases, N is the amount of ideal gases measured in terms of moles and R is the gas constant and T is the temperature. Next, we go for the equation for state for ideal gases. An ideal gas is a substance which obeys the law PV equal to R into T. So, PV equal to R into T, which denotes P is the pressure of the gas and V is the specific volume of the gas and a capital V is the total volume of the gas and R is the universal gas constant, we all know that. So, universal gas constant value R value equal to 8.314 kilojoules per kilogram mole Kelvin. So, R equal to R dash divided by M for any gas. So, T is the absolute temperature in Kelvin. So, PV equal to NMRT. For example, R equal to R divided by M. So, R is a gas constant 8.314 and M for air. So, mass of air equal to 28.97 kilogram per kilogram mole. So, the gas constant value is 0.287 kilojoules per kilogram Kelvin. So, similarly, we have to find out same for the oxygen, right. Next we go for the one important derivation, that is called Maxwell equation. So, Maxwell equation relate the entropy to the three directly measurable properties, that is called pressure, volume and temperature for pure simple compressible substance. From first law of thermodynamics, we all know that Q is equal to W plus del U. So, Q is the heat transfer, W is the work done and del U is the change in internal energy. So, I have to rearranging the parameters, Q is equal to del U plus W. So, we have to apply the TdS equation, TdS equal to du plus PdV. So, we have to rearrange the parameter du equal to TdS minus PdV. We take it as a equation 1. Therefore, ds equal to Q by T. From second law of thermodynamics, temperature will change with respect to the heat transfer, right. So, with respect to heat transfer, the temperature will change. We all know that H is equal to U plus PV from the enthalpy. From that enthalpy equation, H is equal to U plus PV. So, we have to apply in equation 1 dH equal to du plus D into PV. So, W equal to PD by first law of thermodynamics. So, work done equal to pressure into displacement of the volume. So, I mentioned here W equal to PdV. So, work done equal to pressure into displacement of the volume by first law of thermodynamics. So, we have to apply in this equation du equal to du plus VdP plus PdV. Therefore, we have to apply in the dH from the first equation, dH equal to TdS minus PdV plus VdP plus PdV. We have to cancel the plus PdV and minus PdV, right. So, dH equal to TdS plus VdP, it is called second equation. And second, we have to take it as a by Helmholtz function A is equal to U minus Ts, and third function is a Gibbs function G is equal to H minus Ts. By Helmholtz function, A is equal to u minus Ts, therefore, we have to apply dA equal to du minus dTs. We have to apply in this equation du minus TdS minus SdT. So, rearranging the parameters, dA equal to minus PdV minus SdT, that is called third equation of the Maxwell. And we have to, for moving to the fourth equation, by Gibbs function G is equal to H minus Ts, dG equal to dH minus d into Ts. So, therefore, dH minus TdS minus SdT. So, rearranging the parameter dDs plus PdP minus TdS plus minus SdT. So, we have to cancel the TdS plus TdS minus TdS. The equation will become dG equal to VdP minus SdT. So, here just I apply the by inverse exact differential d equal to TdS minus PdV. So, we have to take this first equation of the here I mentioned the fifth equation. This is the first equation of the Maxwell, dou T divided by dou V in terms of S equal to minus dou P divided by dou S in terms of V, right. And the second equation, enthalpy function dH equal to TdS plus PdP. Here the equation 6 will become dou T divided by dou P in terms of S equal to dou V divided by dou S in terms of P. And we go for the third equation dA equal to minus PdV minus SdT. We go for the seventh equation dou P divided by dou D in terms of V equal to dou S divided by dou V in terms of V. We go for the fourth equation, that is called eighth one, dG equal to VdP minus SdT. So, third equation is the Helmholtz function and the fourth equation is the Gibbs function. Here it will become dou V divided by dou T in terms of P equal to minus dou S divided by dou P in terms of T. So, the above the above four equations, the equations 5, 6, 7, 8 are all the Maxwell equations. So, this is an important derivation in this unit, that is called Maxwell equation. The Maxwell equation comes into three directly measurable properties, that is called pressure, volume and temperature. And next one important derivation in this unit, that is called Joule-Kelvin effect, that is called another one the same as the Clapeyron Maxwell equation, Joule-Kelvin effect, Joule-Thomson coefficient. This is one important derivation in this unit, right. So, Joule-Kelvin effect or Joule-Thomson coefficient. So, Joule-Thomson showed that when a compressed gas is forced through a porous plug into a region of flow pressure, there is a appreciable flowing, that is called, we explain in the diagram, thermometers. We have to set in the thermometers and we have to separate the beaker into the diaphragm. So, piston 1, piston 2. So, we have to take a part 1 is the high pressure P1 and volume V1, and second part is the low pressure P2, V2. So, Joule-Thomson effect will shows that Joule-Thomson showed when a compressed gas is forced through a porous plug into a region of low pressure, there is a appreciable cooling. The phenomenon of producing lowering of temperature when the gas is made into expand adiabatically from a region of high pressure into a region of low pressure is known as Joule-Thomson effect. So, when the gas is allowed to escape into a region of low pressure in the molecules move apart rapidly against the intermolecular attractive forces shown in figure. In this case, the work is done by the gas molecules at the expense in the internal energy of the gas, right. So, the steady flow energy equation becomes H1 equal to H2. This is similar to the steady flow energy equation of the throttling device, where the inlet and outlet enthalpy remains constant, right. So, the temperature behavior of the fluid during throttling process is governed by the equation mu equal to dou T divided by dou P in terms of H. So, this is known as Joule-Thomson coefficient. So, Joule-Thomson coefficient is measure of the change in temperature with the change in pressure by dealing with the constant enthalpy process, where here the mu less than 0 the temperature increases, where the mu equal to 0 temperature remains constant, where the mu greater than 0 temperature decreases. So, this is known as Joule-Thomson coefficient. So, Joule-Thomson coefficient describes is a measure of change in temperature by change in pressure by keeping the enthalpy remains constant. that is called Joule-Thomson coefficient or Joule-Thomson effect or Joule-Kelvin effect, whatever the names becomes, that is called Joule-Thomson effect, right. Thank you.